Okay, so, here's I don't think this homework is too bad, not too bad, but it kind of ties together some, ideas we've been talking about. The first one, let's let R be a Hilbert ring, and suppose that R has the property that, every maximal ideal can be generated by K elements. Number A, show that any maximal ideal of R x1 up to xn can be generated by K plus n elements. And next one really isn't worth 4 points, but what the heck, right? So in particular, show that if K is any field, then any maximal ideal can be generated by n elements. Number 2, recall that we defined a Prufer domain R to be a domain such that R localized P is valuation domain for all prime ideals. Show that R is a Prufer domain if and only if every finitely generated ideal of R is invertible. All right, so this is kind of tying together some stuff that we've seen before. Here we're gonna get it kind of into some stuff about fractional ideals and almost integrality. Let R be a domain with a quotient field K. Recall that X in the quotient field is almost integral over R if there is a non-zero R in R such that R absorbs all powers by X down into the ring. Show that X in K is almost integral over R if and only if there's a fractional ideal I of R such that Xi is contained in I. So that's kind of a nice compact characterization, if you will, of the notion of almost integrality. And B, we know that almost integrality is a generalization of integrality. So in number B, formulate a condition on said fractional ideal, I, that assures that X is in fact integral over R, and prove that your condition works. Finally, here's some properties of fractional ideals. Let I and J be fractional ideals of the domain R. A, show that if I is contained in J, then J inverse is contained in I inverse. Show that I is always contained in the inverse of the inverse. And C, show that I inverse is I inverse inverse inverse. All right. So in fact, so those of you I heard kind of talking about it, an ideal is said to be divisorial if you have equality in part B. So that is, if I is equal to its double inverse, it's called a divisorial ideal. So what number C says is that if you have a fractional ideal, its inverse is always divisorial, right? Okay, so that's the fun for next week. Any questions on that? Righty. So if you needed to talk to me today, for whatever reason, just talk to me briefly after class. I've got another delightful meeting at 11:15 that I have to be at. Okay, so let's kind of pick up where we were last time. Any questions from last time? Okay, so the last thing that I left you with, if R is a domain with quotient field K, there exists a one-to-one correspondence right. So there's a one-to-one correspondence between primes of Rx contracting to zero and primes of KX. A key because really, I mean, I'm gonna do this like rather sloppily. Um, this containment should hold whether this is polynomial or power series, right? Because here, sure, right? And it works the other way for polynomials, because if you have A1 over, well, say A0 over S0 plus A1 over F1 X plus AK over SK XK, you can actually write this as A0 prime plus A1 prime X plus AK prime XK over S, where S is S1 by 0 S1 of S. So in other words, you can write this as one just big giant fraction and put it over the single denominator, and then you've got anything that can be spread out written, you can write as a polynomial with coefficients in R over a single denominator, right? It's pretty easy to see from this demonstration that you might encounter problems with power series. And in fact, here's a question, I believe that was answered by Gilmer. When does this hold? Anybody give me an example of multiplicative set that will work?
For how many phases finally generated?
You would probably want that, but actually, that's not good enough either, right? And I would say, how do you mean finitely generated? You mean as a multiplicative set? Okay. Well, here,
In there.
I've got an S that works, S equals 1, that will work. Okay, so I can expand my smart elegantness here by saying S is the units will work, right? What condition you need? For this to hold, you need for all collection of elements A1, A2, and S. So if I take any countable collection of elements from S, I need the intersection of the ideal generated by AI being non-zero.
So we can understand this.
This is an extremely strong condition, right? Extremely strong, right? So for example, even take something very modest, right? Suppose that R is the integers and take S to be the multiplicative set generated by 2. So basically that's about as easy as I can get without just being plus or minus 1, right? So I'm looking at 2, 4, 8. So, you know, the smallest multiplicative set that contains 2. This ain't true because if I look at the countable collection 2, 4, 8, 16, 32, etc., and I intersect those ideals, I get 0, right? So even for that very modest set, it won't work. And essentially, this condition, what this condition does,
That common multiplier, right?
that's right, it allows you to collect a common denominator in the infinite case. That's exactly the condition that you need there. So, in other words, the answer to this is, in a very mathematically precise way, I will state this: almost never. In fact, I think I mentioned last time, generally speaking, you always have, this is always true. This is always true. Let's get a check mark. And generally speaking, these quotient fields are not only different, this one tends to have infinite transcendence degree over this one. So there's, yeah, it's very, very big. Right. So in looking in parallel with what we're doing in polynomials, we see that this key step and what we had last time is a problem for power series. Okay, so that's one thing. But nonetheless, my little soldiers, keep your chins up, stay optimistic, and let's see what happens in the future. Maybe this can be repaired, right? Okay, here's the corollary, and this is, in fact, I'm kind of embarrassed to call this corollary, because this sort of, despite the content of it, deserves to be called a theorem outright. If R is a commutative primitive identity, so suppose R is commutative primitive 1, then there is no chain of distinct primes gamma 0, gamma 1, gamma 2, then Rx all lining over. Actually, I want to be more precisely to what lining over means later, but I'll explain it here. So more precisely, that is gamma I intersect R cannot be the prime P for all you can't have 3 primes contract same prime downstairs. And this particular polynomial range, I can give you ring extensions where there's lots and lots and lots of primes that contract the same prime down below. So, how will we prove this? Well, in the proof of this, there's going to be, again, some more interesting stuff. So let's suppose all have property. Well, let's see for n Rx. Suppose these all have the property that so suppose I have 3 ideals, primes. Have the property that they all contract. one. I'm gonna make my life a little bit easier doing this. I can assume that the smallest one of the three is px. Why?
Because it has at least to contain them.
That's right. Since P0 is contained in gamma 0 as a set, then Px must be contained in gamma 0. And so maybe this isn't the smallest, but I'll just go down and make this the smallest, right? And this allows me to pass to the quotient term. Well, passes to the quotient, right? So, in Rx, we have, so at the Rx level, we have gamma 0, gamma 1, gamma 2, Rx. And these all track P here. Yes,
I have a question, if px is the smallest, all the polynomials that have the constant term in p is like the bigger?
that's that will be maximal containing P, for example, right? So let me make sure that I answer your question in a precise way. P comma X
Right.
will be a prime ideal that is maximal with respect to lying over P, right? So it's the prime ideal of Rx. It is a prime ideal in Rx that is maximal with respect to the lying over that.
So we cannot consider.
But that's not the only one, usually. Right? So for example, let me give you an example here. Let P that will go by 2. Fine. So you might have 2x. You also might have 2, 1 plus x, for example. Right.
Irreducible mod 2.
That's exactly right. All you would need here is this would be irreducible mod 2. Right, and then
The 1 plus x has I mean, I'm saying that fulfill that property that the construction is p.
what's that now?
I'm saying that p comma x generated by p and x is not necessarily the maximal that fulfill the property that the contraction is p.
So if you look at P comma X, that is maximal with respect to this property, but it's not necessarily this ideal, right? Because these two ideals both, if you look at both these ideals, they both contract to 2, right? But they're not comparable, right? Because if you look at these two ideals together, then you've got 1 in it. So there isn't, it is a maximal, not the maximal. So-
Sorry.
Also, so how does gamma not containing P mean that gamma not contains P during the X?
Right, because remember, this is an ideal in Rx, right? So this is a bunch of polynomials. It
Right?
contains this as a set, right? And so if you look at the smallest ideal in Rx that contains P, you get PX, right? So this is already an ideal this is already an ideal in Rx. This is just a subset of this ideal. So this thing has to contain whatever the subset generates as an ideal of Rx. So when I pass to R mod P, and this is then I get 0, gamma 1 prime, gamma 2 prime. Where this is actually gamma 1 mod PX and gamma 2 mod PX. So this allows us to reduce to right? So now we have, let me summarize. R is a domain and all contract to 0. But the previous theorem says there's a one-to-one correspondence. That prime correspond to primes in K. Right? The KX is a PID. So 3 primes cannot be the same. Because PIDs are one dimensional, right? You can't have 2 non-zero primes. Right, so these 3 have to be, the 3 primes cannot be distinct. So notice how slick that is, right? We started from the general command agreement 1, we reduced to the domain and used the previous one by looking at in fact particular PID. This establishes the theorem. So in any command agreement with identity, you can never stack 3 primes in a polynomial ring that all contract to the same prime down below. Everybody okay with that? Okay, question again, does this work for power series?
EX might not be, what we hope it is.
What we hope it is, yes. And actually, I'm glad, Eric, if you asked that question earlier, right? Because this is actually problematic, power series, right? So let me kind of give you, this is a place where things might fail. The first step we took in the polynomial case was by making the efficient assumption, the gamma zero was px. And this is what allowed this reduction, because when I modded out by px, I reduced to the domain case, and that made life easier. Boy, I'd like to do this here. Well, if they all lie over P, it is true that and boy, I'd just really like to say that P power X is contained in gamma. This certainly flies through polynomials, but it doesn't necessarily power series. Actually, it will work from the theory range. Here's all you can say. And this might not even be prime. Right? You can extend the power series. In fact, so let me give you an example to anger up the blood a little bit. I'll talk about this a little bit more. If you have remember the thing we talked about? Right? So I can really think of this as, so if I'm sloppy about it, I can think of this as a field in infinitely many variables, and they're all square and nilpotent, right? Okay. Now, if characteristic of F is equal to 2, then if you look at the idea F and P is x1, x2, so it's the ideal in here just generating other variables, then P R power X is P power X. And worse. If characteristic of F is not 2, then there are infinitely many primes between right? So this is bad, right? You change the characteristic to 3 or to 0, and you're done. And you can actually vary this example by changing the 2's to p's, and then characteristic p is good and characteristic not p is bad, right? So it's bananas. And I'll talk more about this kind of work in a moment. Anyway, so here's the problem. Whereas in the polynomial case, this is px, it worked out really well, allowed us to reduce. Here, px is often very big over. So when you try to mod out and reduce things, you're in trouble because you may have skipped over just a whole boatload of primes, right? Which is obviously not helping your case. So we found problems with localization. We found problems of extending primes to the power series as opposed to the polynomial. But the polynomial keeps moving forward. And so here is the big. Have promised. Let R be community agreement one. And let's suppose that R has crawl dimension n, then okay. This is, I love this theorem because polynomial dimension never gets too big. But it can get this big, and in fact, it's been shown in the literature that this upper bound can be attained. Given P0 and P1 and Pn are, then we've already discussed this, P0x, P1x, Pnx, Pn comma x. In other words, given this chain, I can build one that's at least one longer upstairs. How about the other bit? So we want to show that, we can only bound this, or that basically, and you see where this two comes from, right? Because you can't stick 3 primes over each one of these, right? And so the 2 and the +1 comes from starting to count at 0 essentially. Suppose we have a chain of primes. Now, suppose we have chain of primes. I'll say distinct. Gamma 0, gamma 1, gamma m, nRx. Since there exists at most 2 primes in a chain corresponding PI, well, that means you can have upstairs prime 0, 1 here, then 2, 3, 3, 4, et cetera, et cetera. So this means that M is less than or equal to 2n plus 1. Right. Yeah, because we start counting at 0, that's what gets you up here, right? So this goes 0, 1, 1, 2, all the way up to 2n, 2n plus 1. So, I'm sorry, 0, 1, 2, 3, 2, 3, right, and up to 2n plus 1. Right, we're in, right. Yeah. There we go. Gotta look that up. Okay, any questions on that? Any questions? Okay, so. Same here, or no, actually. So we're gonna get a little bit more into integrality. We're gonna talk about some properties, but this is definitely, um, I'm gonna define the proof of domain a little bit differently than what I did in the notes. You can look at the notes, that's fine, because, I'm gonna do it the way that homework definition. An integral domain. R is proofer if R localized P is a valuation difference. For all P spec R. And I'll go ahead and spoil it for you. Here. So a proof of domain is one whose localization at every prime ideal is valuation domain. You showed in the homework that you don't have to take for all P and spec R, you only have to check the maximal ideals. And the Ethereum proof of domain is called the Dedekind domain. By the way,
You have like, even, you have other things.
Dedekind domains have to be one dimensional or less. Can somebody tell me why? So proof of domains can kind of be all over the place. And in particular, any valuation domains are proof of domain, but more globally, you can make proof of domains by kind of gluing valuation domains together. But then when you go and say, hey, dude, you gotta be Ethereum, that's very strong. In fact, you can't ever build high mountains in Dedekind domains. They all have to be one dimensional or less. Or less than one dimensional fields. So anybody know why?
The height of a prime is, the dimension of our localized, prime, right?
That's right. And so that's the problem really, because if you have a, proof of domain, so suppose you have a Dedekind domain, well, a Dedekind domain, when you localize it, has to be a valuation domain. But when you localize an Ethereum domain, it still has to be Ethereum, right? And the only way an Ethereum, only way that you can have an Ethereum valuation domain is for it to be one dimensional. Right. So, so here are some examples. Let's look at some examples of these. If you look at the ring of all algebraic integers, this is Prufer. Ring of entire functions. On C is Prufer. So that's another good example, rather famous example. Um, but these are a bit of cheat. So. Both are basic, which are. No, I should even do that. Which are basically Prufer domains on steroids, right? Every finite generated ideal is, that principle. Anybody give an example of, a Prufer domain that's. Oh, the ring of integer value polynomials. This is a fun. There are many generalizations of this. I'll just call this withe, which is the set of, how many of you have heard of this? Integer value polynomials. Take a set of elements in QX such that when you plug in any integer, certainly this contains the X, but it's more exotic. Anybody name a polynomial in QX that is an integer value polynomial? So no matter what, if you plug in integer, but it doesn't have all integer coefficients. Here's the easiest example I can think of. And once I do this, you'll probably see how to generalize this. Right? Notice this is a polynomial that does not have all integer coefficients. But if I plug in any integer to this, X is either even or odd, right? So you always get integer value. And of course, I can just go bananas like this, like the factorial polynomial, if you will. So ring is Prufer domain. Can anybody think of here's another one. So basically, this is power series over this field, but I want the constant term to come out of that particular ring of integers. I like this one because it is an example of a Prufer domain that is not Bayesian, right? So it's got finitely generated ideals that are not principal. Let me give you. Let me give you the following theorem, and we'll tie this up a little bit. Actually, I won't tie this completely up because some of it's your homework. Let R be an integral domain. R be an integral domain. The following are equivalent. I'm gonna throw this all in for now. RP is evaluation domain. For all P, press R. 2, RM is evaluation domain. For all M, inspect R. Max. 3, every finally generated ideal of R is vertical. So notice, if you believe me up to this point, so what a Dedekind domain must be is a ring where every ideal is convertible, every non-zero ideal is vertical. And 4, every overring of R is infinitely closed. These 4 conditions are equivalent, and any domain satisfying one, hence all of them, is a Prufer domain. Yes.
For 2, that should be max spec R, right?
Oh, thank you. Yes, it absolutely should be max spec R. I don't know what else to say. Yes. I guess it's true as I wrote it, but it's kind of useless, isn't it? Okay. Any questions on that?
And this ring R here, is the fact that you chose like square root -5 so that you get a class group not equal.
That's exactly what I was saying.
So it makes that harder to.
That reminds me, this week in the math club, Daniel Martin will be talking. He's a fairly new faculty member, and he's a number theorist, so I would encourage you all to be there. He's going to be talking about some interesting stuff in cryptography. So I think you might be interested in what he's up to, and I think it's going to be a really interesting.